Hello and welcome back. In section 2.5 we get to play around with the basic differentiation properties. These are going to give us some nice shortcuts for derivatives. So the first batch of equations we're going to look at, we'll consider y equals 5, f of x equals 8, and let's go back to y. Y equals negative 20. Now remember that the derivative describes a rate of change. Specifically an instantaneous rate of change, but for this group all we have to know is that it's some type of rate of change. Well, if you picture the graphs of each one of these, you should remember hopefully that these are all horizontal lines, one at positive 5, one at positive 8, one down at negative 20, but they are all just horizontal lines. And the slope of a line is its rate of change. Well, a horizontal line has a slope of 0, so in each case we have a derivative of 0. Since these are all flat lines, that's not changing up and down at all. These are a few common notations as well that we use for derivatives. Y prime, f prime of x, or dy over dx. They are all still talking about the derivative of y with respect to the variable x. And there's nothing special about the three constants that I picked. This is true in general, that if you want the derivative with respect to x of a constant c, so c here is just some real number, you will always have a result of 0. Derivative of a constant is always 0. So next, we'll take a look at the idea of the power rule. So we'll start with the limit definition for f of x equals x. By the limit definition, f prime of x is the limit as h goes to 0 of f of x plus h. F of x plus h here is just x plus h, minus f of x, which is x, all over h. Well, here the x's drop, we have h over h, and our derivative is a 1. Next we'll consider f of x is x squared. F of the quantity x plus h quantity squared, which we will end up getting x squared plus 2hx plus h squared. And again, if you want to convince yourself of that, just write it twice and FOIL it. So f prime of x in this case, x squared plus 2hx plus h squared minus x squared all over h. X squared minus x squared is 0. We can also factor in h top and bottom. And again, like before, we want the limit as h goes to 0. H over h is 1. If we let h go to 0, we get f prime of x to be a 2x. I'll run through 2 more of these, and then we'll start looking at a pattern. So the next one will give f of x is x cubed. So take a minute and see if you can find f of the quantity x plus h cubed. Go ahead and pause the video if you need to. Okay, so hopefully in all of your simplifying, you came to f of the quantity x plus h being x cubed plus 3hx squared plus 3hx, or h squared x plus h to the third. Like if you didn't come up with that, the most common cause would be sort of accidentally flipping the order on one of them. I tend to write my h's and x's alphabetical so that it's always in the same order. So our f prime of x this time, limit as h goes to 0 of x cubed plus 3hx squared plus 3h squared x plus h cubed minus the original x cubed all over h. Again, our first term drops. Again, we get a little bit of factoring done. You can pull an h top and bottom. So I pulled an h from all those three terms. H over h is 1, and again we're taking the limit as h goes to 0. So h going to 0 would knock out these two terms. So f prime of x in this situation is a 3x squared. And then our last one before we go for some observations, f of x is x to the fourth. Again, I'll ask you to pause it and see if you can find f of x plus h in this case. So x plus h quantity to the fourth. Okay, welcome back. So hopefully you found f of x plus h. We would have x to the fourth plus 4h x cubed plus 6h squared x squared plus 4h cubed x to the first plus h to the fourth. If you haven't seen the Pascal's triangle shortcut for finding those coefficients when you're expanding a binomial, I'll write down the name again. Pascal's triangle basically starts with this little triangle of ones, and each row you add another pair of ones on the ends, and then every number after that is the sum of the two diagonally above it. So there's where we're getting our 4, 6, and 4. Again, it's just a nice little shortcut, something to check out if you have a moment. It saves you a little bit of time expanding binomials. So here, f prime of x, again, the limit as h goes to 0 of this whole mess that we just found, x to the fourth plus 4h x cubed plus 6h squared x squared plus 4h cubed x plus h to the fourth. We subtract our original x to the fourth and divide by h. First term, as we've seen each time, drops out. F prime of x, limit as h goes to 0 of factoring and knocking out our h top and bottom. Well, we're left with 4x to the third plus 6hx squared plus 4h squared x plus h cubed. However, h going to 0 knocks out all three of these remaining terms, and we get f prime of x to land on 4x cubed. Pattern time. f of x is s is equal to just x. F prime of x was 1. We had f of x was x squared. F prime of x was a 2x. F of x equals x cubed. We got to f prime of x is equal to 3x squared. And our last one, f of x, was x to the 4th. And we got to f prime of x was a 4x cubed. So hopefully you remember that from your previous couple pages. So our 1, our 2x, our 3x squared, and our 4x cubed. So now I want you to sort of make a prediction on what would happen if we had f of x is x to the 5th without having to expand it all the way out. Predict what you think f prime of x will look like for this guy. While you're thinking of it, I'll leave a little hint here. X to the 0 is worth 1. So hopefully you notice the pattern that our exponent became a factor. So 5 will be a factor. We hang on to our base, and we simply subtract 1 from each exponent. And that is true in general. If we have f of x equals x to the k power, then f prime of x is k times x to the k minus 1 power. This is for differentiable values of x. So same rules before things that aren't differentiable. If we have things like a cusp or a corner or a hole or a jump, at those values, this rule doesn't hold anymore. But anywhere where we are differentiable, such as over here, before or after that break, before or after that cusp, corner, hole, jump, whatever, then we're allowed to use that. Okay. Now, where that comes in handy, rational exponents as well. If they tell us that g of x is the cube root of x squared, that one's a little bit messier if we do it the older way, but if we just take one moment and turn this into an exponent from a radical notation. So this is still known as g of x. I have not turned this into g prime yet. This is still just g of x. It's x to the 2/3 power. You remember that from your Math 100 and Math 165 days. X to the 2/3 power. So the exponent stays the exponent. Index becomes the denominator in the exponent. After that, if we want the derivative, we just follow this same pattern. So then g prime of x, exponent becomes a factor. Hang on to your base and subtract 1 from your exponent. So 2/3 minus 3/3 is negative 1/3. So instead of thinking of that as minus 1, think of it as minus 3/3 because our denominator was 3. If it's a square root, think of it as minus 2/2, etc. That also comes in handy with rational expressions, rational functions, I should say. If I want 1 over x to the 20th, I'll take one moment and rewrite it as x raised to the negative 20th power. After that, then I can just apply my rule from before. The exponent is now a factor of negative 20. Hang on to your x. Subtract 1 from your exponent. Careful here with your signs. Negative 20 minus 1 is negative 21, not negative 19. Just kind of watch your signs on those. All right, so I'm going to give you a couple to sort of try out here before we move to the next property. So we'll try y is x to the 12th. F of x is the 5th root of x. G of x is 1 over the 7th root of x. Y equals pi squared. H of x equals e. That should be enough.